Hello physics students. Welcome to Mental Exercises, Creating and Understanding Graphs. At this point, you should have already printed out these sheets. On these sheets, what you're going to be doing is you're going to be drawing graphs based on some motion that you see. And then I'm going to use a computer to show you the actual graphs. Now, how is the computer going to generate graphs of the motion? Well, what I have here is what's called a motion detector. When I turn it on, what it does is it makes a bunch of clicks. Let me turn it on. And maybe you hear that. And then you see when I go like this, look at the graph. And then when I go like this. So what is happening here? Let me stop this. So what's happening is this is sending out click after click. And sound is a wave like all waves that travels. And when it hits something, it reflects. And in the case of sound, we call that an echo. So that sound goes up, hits the ceiling, comes back to the motion detector. So the motion detector makes a sound and then listens for it. Based on how long it takes the sound to return, it can tell how far away an object is. The longer it takes the sound to go and come back, the further away the object is. If it takes a very short amount of time for the sound to go there and back, well then obviously the object is close. So from that, it can plot how far away something is as a function of time, create a nice graph. It can also plot velocity and acceleration through some calculations done on the computer. So what I'm going to do is I'm going to set this up like this, and then the first part, the first series of graphs, what we're going to be doing is we're going to be studying constant velocity motion, uniform velocity as the Regents likes to say. And to study that, I have this nice little cute little toy, a little bulldozer with a motor that lights up. I can make it go in one direction, I can make it stop, or I can make it go in the other direction. So that's what the motion detector is going to be measuring. Okay, so let me clear this data run here. Okay, so in the first exercise here, it says consider a person walking away from a motion detector at a constant speed. All right, it's not a person, it's a little toy, but it's going to achieve the same thing. So this is what's going to happen. I'm going to turn the motion detector on, and then I'm going to walk over here and let this go, okay? And you're going to draw the graph. So sketch it now, okay? And I know when we're doing this in class, I have to really fight students. More than half the class just waits, and they figure, well, I'll just wait till I see the graph, I'll fill it in. Then you're not learning, okay? The idea of this activity is that you sit and you think through it, and then you draw the graph, and maybe you make a mistake. But then when you see the correct graph, it'll be that much more powerful for your learning, because you'll learn based on what you tried, and you'll maybe start thinking about why you thought wrong, and you'll learn a lot more that way. So when we have everyone in class, what I do is I actually walk around and I don't show the graph until everyone's drawn a graph. So I'll pause the video now, and then I'll start it back up, and then I'll show you what the graph should look like. Okay, well, let's see what the computer shows us. I'll start the machine, and I'll turn it on. And there we see the graph being formed as that bulldozer or whatever it is going away from the motion detector. Now, before you sketch the actual graph, what I want you to draw in this area is your axes right here, because this is me walking over to turn the machine on, right? So I hit the thing to start, and then I had to walk over here, We're not interested in that. We just want this. Y-axis, x-axis in a diagonal line like this. So maybe you had this as a prediction, and then you would fill in the actual like this. So Again, so maybe you guessed that it would be a curve like this, but that's okay to be wrong. You sketch in the actual here, a straight line up like that, okay? All right, now, don't be bashful. I'm going to pause the video to give you a chance to predict the velocity graph, okay? So go ahead and do it. Okay, so let's take a look at what the computer is going to show us here for a velocity graph. All right, now, this I don't want you to draw. Again, this is me. I'm walking over and the thing's staying here and I haven't turned it on yet. So now it starts moving. Then there's some squigglies because, you know, the motor's not great and so maybe hits a little bump on the table. We're not concerned about these little squigglies. What we're interested in is the trend. And the trend is a line that goes straight across like this. Constant velocity, right? So maybe you thought the velocity graph went up like this and then you draw in the actual like this, okay? So, all right, so again, whatever, maybe you predicted right? But you drew this before, now you're drawing what's after. Again, this is my prediction. I'm purposely predicting wrong. Maybe you got it right, but that's how you do the activity. You predict this before I show the graph and then you draw this. Okay, number 2 says, on the same graphs above, draw the motion for an object moving slower. I'll pause the video, draw both graphs, a hypothesis in your prediction areas, and then I'll show you the actual. Okay, so the actual graphs, I'll do it in maybe red ink so it shows up. Okay. And here it is. Okay, so you see slower is a line that begins at the origin but slopes up at a slower slope, and then slower is still straight across but lower for velocity graph. Now just a reminder, there's a couple ways to interpret and figure out this velocity graph based on this. One way you could say, all right, the velocity is constant. That's how I draw something straight across. This would be increasing velocity, decreasing. No, staying constant. So that's a physical way to generate this graph. The other way is to realize the slope of this line is the velocity. And if you draw a little circle right here, that line has the same slope here, here, here. Everywhere it has the same slope. The same slope. The slope doesn't go up or down. It's the same slope. So 2 different ways to think about it. All right, let's move on to number 3 here. Okay, it says, consider a person walking toward the motion detector at a constant speed. So now what I'm going to do is I'm going to begin this over here. I'm going to start the thing ticking, and then I'm going to go like this, all right, and direct it straight at the motion detector, okay? Steady, steady, steady towards the motion detector. Again, don't be bashful. Make a prediction, okay? So I'll stop the video, sketch something in for the distance graph, okay? All right, let's see. Let me clear the data here. And set up my car. Okay, there it is. Start. And there it is. Okay, let me stop the machine. Okay, so again, this is me walking over. What you want to draw is like the axis like this, starting up high. The other one started here because it started near the motion detector, went away. This one starts far away and goes straight down. So whatever your prediction is, the actual should look like that, okay? Starting far and getting close. Okay? All right. I'll pause now. Go ahead and predict the velocity. All right, let's take a look. I'll show you. And again, we're not worried about this part. This is me running over and turning it on, and then maybe I held it back for a little bit. Imagine the axis right here, straight across negative, okay? So that would look something like this, okay? The actual. All right, so straight across below the t-axis. And again, I hope you're filling in predictions, right? Otherwise, it takes all the fun away if you don't make any predictions. Okay, so a couple ways to interpret this. One, you could say it's going backwards towards the motion detector. If this was positive velocity, this has to be negative velocity. So now I'm below the axis. And this is going at a steady pace. It's not speeding up or slowing down. It's going the same speed across. That's one way, physically. The other way is mathematically. You realize this graph is the slope of this one. And if I look at a region right here, or here, or here, it's the same slope everywhere. So same slope everywhere, same velocity, okay? And negative slope. So, all right, number 4, create the graphs for a person moving faster in number 3. So go ahead on both these graphs, make a prediction. Someone goes, or a car, maybe I juice it up with more batteries, and this goes off fast, okay? That's my alarm clock at school, or clock, it chirps birds on the hour. So that's what that is, if you're wondering. All right, so I'll pause the video, predict those graphs, and then I'll show you in a second. Okay, so let me sketch these in. All right, so here they are. What you would do is you would start this farther, just at the same point, but it slopes down faster. Bigger slope, bigger speed. And this velocity is even more negative, but constant straight across, okay? All right, number 5. Number 5 says, consider a person who walked away from the motion detector, paused, and then walked toward the motion detector. So here's the motion. I'm going to set the machine on, and then I'm going to go like this. And then somewhere around here, I'm going to shut it off. And I'll wait a couple seconds, so I'm pausing, okay? And then after that, I turn it on to go back, okay? So, again, predict the displacement graph. Do it. Again, don't just wait, okay? So I'll pause the video, give you a chance to make that prediction. All right, let's see what the computer says. Oh, I didn't quite line this up properly. Let's do a little better job here. Okay. All right, ready to go. And I'm waiting. Okay. And then I'll let it return. Uh-oh. I think I'm going to have to do this again. What happened was sometimes the sound misses the car and it goes and hits the wall, and that's why we see that spike. You already see the pattern, but it'll make the velocity graph a real mess if I don't redo this again. So let's see, what could have gone wrong? All right. Let's see if we've got better luck now. Oops, Missed the button. Missing again. Maybe it won't be too bad. Okay. Okay. All right, so let's see, maybe we'll still have an okay velocity graph. But again, we want the axes to start here, and we've got a straight line like this, a flat region while the car is stopped, and then this is when it's going backwards. Okay, so what you should see for the actual is this right there, okay? This is when it's moving away at a steady pace. This is while it's stopped and waiting, and then coming back, okay? All right, go ahead and make a prediction of the velocity graph. I'll pause the video. Okay, let's see what the velocity graph looks like. Not bad, okay. So what we see is like a plateau here, and then it's a zero plateau, and then a negative plateau, okay? So something like this. Okay, so positive plateau, zero plateau, negative plateau. Okay, and this should roughly align with those transition points. Okay, so the interpretation. One, we could say constant positive velocity as it's moving away, so that's constant positive velocity. This is zero velocity because it's stopped, so it's stopped, zero velocity. Then it's going the opposite way of when it was going positive, so this is now negative velocity and constant. Okay, so that's a physical sort of reasoning. The mathematical reasoning is to look and see the slope of this line is positive, not negative, and it's the same slope, it's not curving. Okay, so same slope, so same positive velocity. This is a zero slope, right? It's not sloping up or down, not positive or negative, it's zero slope. And this is a constant negative slope there, okay? So those are the interpretations. Okay, the next one, number 6. Consider a person who walked towards the motion detector, paused, then walk towards again. So, starting here, I'll start the ticking, and then I start this towards, and then maybe right here, I stop it and sort of wait for a while. So it's still ticking, but I'm waiting. And then, after an amount of time, I resume the motion, and that's it. Make your prediction, okay? And I'll pause the video to give you a chance to do that. Okay, so let's get the computer to show us the actual graph. There it is, okay? So here's your axes, and you've got a straight line like this. That's it coming toward, when it was first coming toward, then it stopped and sort of waited here, and then it started coming toward again, okay? So the ideal graph, idealized graph should look like this, Oops, wrong. All right. So sketch that right there. Towards, stopped, towards. Okay. All right. Time for the velocity graph. So I'll pause the video, give you a chance to sketch that. Okay, let's see what it looks like. All right. So again, we've got to sort of look at taking away the little squiggles of the data, but the axes will start right here. So negative, constant, that's this. Then 0, it's not moving. And then negative again, because both times, first it moved this way, which is negative, then it stopped, and then it moved in the negative direction again, constant velocity in each case. So something like this. Okay, like that. Negative, 0, negative. By the way, some people ask, if you were in class, you might be asking, well, what if I put lines like this? And that's fine. You could do that. It doesn't really change the graph much if you connected those regions like that. Perfectly fine, still correct. All right, so quickly, the interpretation. I already gave you the physical one. The mathematical one is if you look at the slope anywhere here, it's the same steepness, so, and it's negative. So the same slope negative. If you look at the slope here, or here, or here, or here, it's 0 in all these places, a constant 0 slope. And then finally, negative slope again, that's the constant. So that is the motion. All right, so I believe we do the next set of graphs, the acceleration, on another day. So I'll stop this video here. But I just want to call your attention to the patterns. If you go back and you look at all the displacement graphs, okay, there's a key feature to all of them. I'm going to pause the video. You go back and look and see in your mind, if you could write a sentence, what would you say about all the displacement graphs for something moving at a constant velocity? All right, I'll pause and give you a chance to think it over. All right, what you should have said is that the displacement graphs are all linear. Maybe they slope up like this, maybe they go straight across for not moving, or maybe when it goes backwards it slopes down. But there's no curvature to any of the displacement graphs. Now, look back at the velocity graphs. See if you could state a sentence that captures the pattern of all those. I'll pause the video, give you a chance to do that now. Okay, you should have said that the velocity, when the velocity is constant, the velocity graphs are always horizontal lines. They do not go up, they do not go down. They're either above the t-axis, so here's t-axis, and then it's like this, and it's going forward, positive velocity constant, or it's on the t-axis, then it's not moving, it's stopped, constant velocity of 0, or it's below the t-axis, straight across, and then it's moving backwards in the negative direction, but a constant state. It does not go like this. So those are the patterns. Hopefully you got them down and you did do the predictions and then the actual, and so you learn how to do these graphs, and now hopefully you're experts at drawing graphs. All right, I'll see you in the next one where we look at the graphs for acceleration.